All right, let's dive into an incredible story. We're going to go on a journey that spans more than 2,000 years, all to understand the one thing that makes up, well, everything. We're talking about the atom.
This is one of the biggest, oldest questions we've ever asked ourselves. If you take a chair or a glass of water or even the air you're breathing, and you keep cutting it into smaller and smaller pieces, what do you end up with? This single question has driven so much of science and philosophy for, well, millennia.
So, where does our story begin? Like a lot of big ideas, we have to go way back, all the way back to ancient Greece, where a huge debate was just getting started. So you had two camps. In one corner, there was this guy Democritus. He had a pretty wild idea that everything was made of tiny, indivisible, uncuttable particles he called atomos. But in the other corner was Aristotle, and he thought everything was just a mix of four things: earth, air, fire, and water. Now, Aristotle is a super influential guy, so his idea, it stuck. It was considered the absolute truth for almost 2,000 years. Okay, let's fast forward a long time. It wasn't until the 1800s, with the scientific revolution in full swing, that the idea of the atom made a major comeback. This kicked off an amazing chain of discoveries, each one building on the last.
The first big player in this new era was an English schoolteacher named John Dalton. He brought back the atom, but this time with actual science behind it. In his mind, atoms were just tiny, solid, indivisible spheres. The easiest way to picture it? Just think of a billiard ball.
Dalton's theory was a total game changer. It gave chemists a set of rules to play by. All matter is made of atoms. Atoms can't be created or destroyed, and in a chemical reaction, they just get rearranged. Simple, elegant, and a fantastic starting point. But it wasn't the whole story. You see, there was this one big mystery that Dalton's little billiard balls couldn't explain: electricity. We knew you could, rub a balloon on your hair and make it stick to a wall. But if atoms were just neutral little spheres, how could anything become positively or negatively charged? So along comes J.J. Thomson in 1897. He's doing these experiments with something called a cathode ray tube, and he discovers something that just blew everyone's minds. He found a particle that was way, way smaller than an atom, and it had a negative charge. He had just discovered the electron. This totally changed things. To make sense of it, Thomson came up with what we call the plum pudding model. The idea was that the atom is this big ball of positive stuff. Think of it like a blueberry muffin. And the negative little electrons are like the blueberries scattered throughout. This was huge. For the first time, we realized atoms might actually be made of even smaller pieces. Now, this led to a really interesting question. If an atom is really this soft, squishy muffin, then shooting tiny particles at it should be like firing a BB gun at a cloud, right? The particles should just zip straight through. Well, a scientist named Ernest Rutherford decided to actually try it. Rutherford's experiment was brilliant. He took this super thin sheet of gold foil and fired a stream of tiny positive particles at it. He fully expected them all to just sail right on through, and, well, most of them did, but some of them, about 1 in every 8,000, bounced. Some even bounced almost straight back. It made no sense. The results were so bizarre, Rutherford himself put it perfectly. He said it was as incredible as firing a cannonball at a piece of tissue paper and having it come back and hit you. Something was seriously wrong with that plum pudding idea. This shocking result led Rutherford to a radical new conclusion. The atom wasn't a soft pudding. Instead, almost all of its mass and all of its positive charge were packed into an unbelievably tiny, dense center, which he called the nucleus. And the rest of the atom? It was almost entirely empty space. So Rutherford's model was almost there. He figured out there were positive particles in the nucleus, we call those protons, but the math for the atom's weight still didn't quite add up. The final piece of that puzzle was found in 1932 by James Chadwick, the neutron, a particle in the nucleus with mass, but no charge at all. Okay, so we've got a nucleus with protons and neutrons, and we've got electrons zipping around on the outside. But what exactly are those electrons doing? How are they arranged? This is where the Danish scientist Niels Bohr enters the story. Bohr was fascinated by light. He noticed that if you heat up an element, it doesn't just glow. It gives off very specific colors, like a barcode of light. He had this brilliant insight. What if that meant the electrons couldn't just be anywhere? What if they had to stick to fixed orbits or energy levels, kind of like planets around the sun? The specific colors he saw were just the light that an electron gives off when it jumps from a high orbit down to a lower one. Phew, okay, that was a whirlwind tour of discovery, right? Let's pause for a second and just lock in what we now know about the basic parts of an atom. Consider this the owner's manual. It really boils down to 3 key players. You've got your positive protons and your neutral neutrons hanging out together in the center, in the nucleus. And then, orbiting on the outside in those energy levels, you've got the tiny negative electrons. That's the basic setup. And we can describe any atom with 2 really important numbers. The first is the atomic number. That's just the number of protons, and it's like the atom's social security number. It defines exactly what element it is. If it has 6 protons, it's carbon, period. The other number is the mass number, which is just the protons plus the neutrons. Pretty straightforward. Now, understanding one atom is great, but the real magic, the part where we start to understand the whole universe, is when we start organizing all the different kinds of atoms. This was the next huge challenge for scientists. By this point, they discovered dozens and dozens of elements. How do you organize them all? How do you lay them out in a way that doesn't just list them, but actually shows you how they're related? The answer, of course, is one of the most beautiful and powerful tools in all of science, the periodic table. It turns out, if you just line up the elements by their atomic number, by how many protons they have, these incredible patterns just appear. But why does it work? Why do those patterns show up? The table isn't just a random arrangement, it's a map. And it has a secret code. So let's crack it. The whole secret, the key that unlocks the entire periodic table, comes down to a special group of electrons. We call them the valence electrons. These are the electrons in the outermost energy level of an atom. They're the ones on the frontier, the ones that actually interact with other atoms and cause all the chemical reactions. They're the most important ones. So, take a look at the very first column of the table. Group 1. You've got lithium, sodium, potassium. They're all different elements, but they behave in a strangely similar way. They're all soft metals, and they all react, let's just say energetically, with water. Why? What do they have in common? The answer is 1. Every single element in that column has exactly 1 valence electron. Just 1 lonely electron in its outer shell. And that 1 electron is what makes them all behave so similarly. Okay, let's see if this pattern holds up. Let's jump way over to the other side of the table, to group 17, the halogens. We've got fluorine, chlorine, bromine. Again, totally different elements, but they're all super reactive nonmetals. What's their secret? You guessed it. They all have the same number of valence electrons. In this case, it's 7. Every single one of them has 7 electrons in its outer shell. This is not a coincidence. And this is the absolute genius of the periodic table. An element's column, its group, tells you its number of valence electrons. And the number of valence electrons determines almost everything about how that element is going to act. The table isn't just a list, it's a cheat sheet for chemistry. It's a blueprint for chemical destiny.
So when you step back and look at it, we've gone from a simple philosophical idea of an uncuttable particle all the way to this complex, beautiful model that explains so much about our universe. It's really an amazing testament to human curiosity. And the story is not over, which, of course, leaves you wondering, what are we going to discover next?